A very good day to Dr. Haslinda, Dr. Serene, and Dr. Siti Haja. I'm Jia Sen. Today I'm going to share about my FYP2 presentations with the title of Modified PID Controller for Improved Control Loop Performance under Stiction's Nonlinearities. In today's sharing, it will cover introduction, literature review, methodology, result discussions, and conclusion. Without further ado, let's move into the main topic today. First of all, we will begin with the introductions of our topic today. The presence of control valve nonlinearities like Stiction's backlash and deathband is a major cause of the oscillations in the control loops. Among the most types of nonlinearities in control valve, Stiction's is the most common and one of the long-standing problems in the process industry. The presence of oscillations in the control loop increases the variabilities of the process variables, thus causing inferior quality products, larger rejection rates, increased energy consumptions, reduced average throughput, and decreased profitability. There are some proposed solutions in order to solve the valve Stiction's issues. The best solution is to run the maintenance and repair on valve, but it is only possible for a long period. Hence, the changes on the traditional algorithm and structures of PID or compensation methods have been introduced to reduce the occurrence of Stictions until the next maintenance. However, the current compensation methods require many predefined parameters in the settings before the operations. Therefore, it comes to our objective today. My FYP basically will mainly cover two objectives. The first objective is to reproduce the most recent PID-based compensation methods, which is the novel Stiction compensations model, and evaluate its performance under different scenarios such as set point tracking, disturbance rejections, varying noise level, and random set points. Then, we will compare our model with his article results. The second objective is to modify and improve this compensations method by reducing the amount of required predefined parameters using neural network and evaluate this developed neural network model under the ManSpark simulation studies. Before moving on to the project details, I will introduce and share some brief knowledge about this topic in the literature review section. Among the PID-based compensation methods, we can separate them into three different types, which are retuning PID, modified PID, and augmented PID. PID controller retuning used in the process control loop is able to significantly reduce the amplitude and frequency of oscillations by tuning or finding the most optimal parameters for the controller settings. Newton-Raphson's method is one of the solutions to apply in the retuning of the controller to improve the performance of Stiction's compensations. Next, the second existing PID-based compensations methods is modifying the traditional PID algorithm without adding any extra compensator. The points listed below the modified PID are the methods that have been found. Modifying the PID controller without using any additional compensator would be a good option for the industry to solve the nonlinearities problem on behalf of valve Stictions because it can reduce the overall maintenance cost. Lastly, adding a compensator block to the PID controller, also known as augmented PID, will be another approach of the PID-based compensations methods. This method will be our main focus today since it can guarantee the disturbance rejections and set point tracking in the control loop and remove the impact from the sticky valve. There are 8 different types methods and the comparisons will be made among them. Moving on, we will discuss the mechanism of novel compensation methods, which are the most recent augmented PID-based compensation methods. The compensator will receive two signals, which are control error signals E and controller output signal UC. If the valve stem becomes stuck at the fixed positions, means no output from valve, the error signal keeps increasing. When the error signal reaches the predefined limits, the pulse generator inside the compensator is activated and it will generate the pre-designed pulse. In this compensator, two outputs will be generated here, which are the compensator output with pulse and reduced control actions. This is the algorithm shows how novel compensation methods works. Two input signals will enter the compensator. The system will check whether the error signal is greater than the predefined threshold epsilon. If the control error is less than epsilon, the TP, which is the start counting time period, will be 0 and proceed to the output with the equation dividing by the detuning parameter. Else, if the control error is greater than the predefined error limits, it means that the valve stem starts at its fixed positions. After that, if TP is greater than the specific time limits, means that the valve still remains stuck at the fixed positions. It may send the signal to the pulse generator where the pulse will be added to the output signal. If TP is smaller than TG, means that the valve can already move and functions. then it will return and proceeds with the normal output signal. Hence, basically, this is how the compensator works. These compensator methods require the usage of the simple pulse generator and the tuning parameters A, which is the only parameter needed to be specified each time depending on the controller and the process. Even though the compensator methods like novel compensation model enable to provide an excellent performance to handle the stiction issue, it still requires a lot of predefined parameters which may vary depending on different situations such as the detuning parameter as we mentioned previously. It requires to be obtained after thousands times of trial and error steps, and this value may change according to different situations. Therefore, the neural network time series model is then proposed. This is one of the deep learning methods to be proposed for time series forecasting instead of traditional forecasting methods like box, Haskins, RMA, and ARIMA. This is because those classical time series predictions methods are facing the inherent limitations which are only treating the linear relationship between inputs and outputs. Since the warp dictions is the typical nonlinearity problems that occur in the flow of controller along the time, neural network time series model is the most suitable artificial neural network ANN model to be implemented. No predefined parameters are required for this model, and we only need to train it with the current accurate time series data, and in the end it is able to handle different situations of the sections by its own. Therefore, without any hesitations, let's see how it works in our methodology. This is the redeveloped novel compensation model. In this model, the previous mentioned parameters such as the detuning parameter, permissible error, control signal, or pulse generator will be added to the method functions. The algorithm of the model will be represented by the coding as shown in the diagram. Therefore, when there is the high station detected in the control loop, the pulse generator will create extra pulse to reduce the control action in the system. However, this compensator will cause the output of the process goes to the lower values before entering to its steady state position. To overcome this problem, the compensator output needs proper initializations by adding the gain block. The initializations is using the average steady state value of the controller output immediately before starting of the compensator. Such initializations enables the compensator to mitigate the stiction effects without creating much upset during the switching. Next, the model with initializations becomes a model that will be applied and tested under different scenarios. There will be 4 different scenarios similar to non-hit research, which are the set point tracking, disturbance rejections, varying noise level, and random set point. The setup of these scenarios are shown in the diagram. After testing on different scenarios, the compensator is further improved and modified according to its weaknesses. The extra PI controller tuned by GA is being added and the random set point block parameters is changed. Also, 2 extra switch blocks are added to the control loop. The performance of this modified compensator model will be shown in the result discussion part later. After that, the data from the latest model is being extracted with 500,000 seconds to train the neural network time series model. One of the neural network time series model NARX block is now replacing the previous novel compensator in this control loop. The NARX model is chosen among all other models since its input vector can build through 2 tap delay lines, where one sliding over the input signals together where is the signal of the controller and another sliding over the network's desired output where is the set point signal. After that, in order to reduce the high amplitude spike occur in the result of NLRX model, the saturation block is added. The upper limit of saturation block are set to 3.72 while the lower limit of saturation block are set to -1. In the end, the developed neural network can be tested under the benchmark simulation study. The benchmark simulation study will be distributed into 2 sections, where the first sections will be the detailed comparisons of parameters in transfer functions, and the second sections will be the case studies. The first sections will cover the gain, time constant, and time delays of the transfer functions and the dictions amount. The second sections will cover the well-tuned controller, controller with excessive interactions, with external oscillatory disturbance, and with presence of dictions. This will be our first section benchmark simulation study, and this will be the second section benchmark simulation study. Moving on, let's review the results of the simulations that I have done. First, this is the results of the control loop without the compensator affecting by dictions. Based on the result, the diction has hindered the warp movement and caused the oscillations. After adding the compensator, this is the results that are obtained. The compensator is used to reduce the contractions and add the additional power when the system is needed. When the start of the compensator, the input signal to the valve at the switching times will create some process upsets. The process output response curve shown here are the typical case when the compensator starts to activate at 4000 seconds. The output at 4000 seconds will move to lower value than the previous oscillations. The bottom result has successfully imitated non-hit results as shown at the top. To solve this problem, as mentioned before, the output of the compensator requires initializations by using the average steady-state value of the PID controller output before the compensator starts working. Therefore, the result here shows the process output response curve without the huge oscillations after the initializations by adding the gain block after the compensator. Moving on, we have started to test the model under different scenarios starting with the compensator with initializations. The set point changes in upward and downward directions and the result have shown here. The process variable enables to track and trace the changes of different set points. The second scenario is the compensator with disturbance rejections. The disturbance is able to deviate the output results from its set point. The step input types of the disturbance have been added to the control loop and cause the deviations at 7000 seconds. The results here shows the compensator could reduce and eliminate the oscillations due to disturbance effectively in the short periods. Next, the performance of compensator is evaluated by varying the noise level. According to the results, the compensator enables to reduce the durations of oscillations caused by white noise. Thus, it could be said that the compensator can function well and effectively under varying of noise level. Lastly, it comes to the evaluations of random set point. According to the results at the top, the process variable can track the random set point change successfully. However, there are some oscillations occur. Thus, the compensator is being modified and further improved. The result shown at the bottom clearly has removed the oscillations in the controller. Therefore, this data from the result will be extracted to train the neural network. To develop the neural network model, 70% of data is being trained, 15% of data is being validated, and another 15% of data is being tested. In order to analyze the effect of using different data sets, the result of 160,000 second trained data and 500,000 second trained data are compared, and obviously the result of 500,000 second is much better since there is no oscillatory curve at the first 20,000 seconds. Therefore, the greater the amount of trained data, the more accurate the neural network training results to the original data. From the previous slide, we can observe that the amplitude of the PV curve starting at every new set point is very high. In order to solve this issue, the saturation block is added by reducing the high amplitude spike. There are two different settings of the saturation block shown here. Based on the result, obviously, the saturation block with maximum limit of 3.72 provides a better result with the oscillations at 10,000 seconds to 20,000 seconds. Thus, we can proceed the benchmark simulation study with this setting. The first benchmark simulation study, starting with sections 1 with different gain value being tested. According to both results, there is no huge difference among the result of gain at 45 and 55. Therefore, we can conclude that the NLRX model has not affected when approaching to the changes of gain in transfer function. Next is the different time constant among the simulation result of the control loop with time constant at 90 and 110. No huge variations is found. Therefore, we can conclude that the changes in the time constant of transfer functions will not bring any effect to the performance of NLRX model. Coming up is the different time delay. According to the simulation result of the control loop, the overall trends of the result for both different time delay is exactly similar. Therefore, it can conclude that the changes of time delay may not affect the performance of NLRX model. The last testing on section 1 is on different stiction amount. Based on the comparisons on the low and high stiction amount, the performance of NLRX model is good when the stiction amount is low. However, the oscillations on the high stiction amount is able to maintain under the acceptable range, which is 50 to negative 50, and the PV curve after oscillations is returning to normal. The oscillation periods is controlled under 10,000 seconds, which may slightly affect the sensitivity of the control loop. However, the NLRX model is still functioning well in mitigating the stiction and turning back into the steady state. Moving on is the section 2 of the benchmark simulation study. The top result shows the best conditions of control loop with NRX model. From the result, the spiking jumps occur at every start of new set points. This is because the neural network will predict the trend of the time series result according to the train data, since the same characteristic has shown in the previous extracted data that we used to train and apply in this NRX model. The bottom result shows the control loop with excessive integral actions controller. Based on the figure, the trend of Bill curve is found similar with the result from well-tuned controller. Therefore, it can conclude that the excessive integral actions controller will not affect the performance of NRX model. The third case study is the control loop with external sinusoidal disturbance. The continuous oscillations occurs and the Bill curve is totally not following the trend of the setpoint curve. Thus, it shows the limitation of NRX models when facing the external disturbance applied to the control loop. Lastly, the result shows the control with presence of stiction. It shows the exact performance with the well-tuned controller. Thus, NRX model is still able to mitigate the stiction amount up to this level without showing any variations in the simulation result. In the summary of benchmark simulation study, we can conclude that the neural network model is slightly affected by a very high stiction amount and is not able to handle the controller with external oscillatory disturbance. Finally, it comes to the end of the presentation today. In the conclusion, the developed model is able to get the similar result for different scenarios as compared to Naive model. However, this model is still require a lot of predefined parameters such as the detuning parameter or the game blocks parameter. Thus, the neural network time series model is implemented to replace the current compensation model. It is found that this NARX model has outstanding performance in sensitivity and robustness under the benchmark simulation study. Before we end the presentation today, there are some recommendations for the future study of this project. The extent study are required to remove or further reduce the high amplitude spike at the neural network time series model. Besides, the current model is not able to handle the situation when extra oscillatory disturbance is added, and thus the extent study is needed. And this comes to the end of the presentations, and that's all from me. Thank you.